Hi, welcome back to Kiersti's virtual classroom. Today we are talking all about sedimentary rocks. So let's get into it. So we've been talking about rocks so far. All we've talked about is igneous rocks. We have two other rock types to talk about, that's sedimentary and metamorphic rocks. So you're going to be working on a rock cycle. So I would save this or draw your own, and we're going to be filling in some of these pieces that are missing. So with igneous rocks, we know that they are formed from magma that has cooled and solidified either below ground or on the surface. Now we're going to be talking about how we form sedimentary rocks, which will be this next box we're working on. Okay? So in order to make a sedimentary rock, this all happens on the surface. I know that we talked about igneous rocks. They all form from deep magma below the surface, and some form on the surface and some below. All sedimentary rocks are formed at the surface, and they are primarily about 80% of the rocks that you actually see on the surface. They don't make up much of the crust, only about 5% of it is sedimentary rocks, but most of what you see on the surface is sedimentary because everything starts to weather once it's exposed at the surface. So most of what you end up seeing is sedimentary. Okay, so these are the steps in forming a sedimentary rock. So the first thing that has to happen is weathering. So this is the breakdown of the rock as it sits in its current position. So if you see a rock that is attached to a cliff face, it is actively being weathered. So that's the first step to start forming a sedimentary rock. Now, once it is removed from the parent rock or the rock that it started at, it is eroding. Okay, so weathering and erosion kind of go hand in hand. Weathering has to start the process of breaking down the rock, and the erosion is the removal of the rock from its original parent rock. Okay, then those pieces get transported. So they can be transported by gravity, wind, water, or ice. And then the transportation method will take it to its depositional setting. And so the depositional period is where it settles out. And usually this happens in a fluid. Sometimes it happens in air. A lot of times it happens under lakes, streams, rivers, the ocean, wherever the depositional area happens to be. And the final stage is what we call lithification. This is where compaction and cementation occur. And so the rock goes from being just particles of an older parent rock into a new sedimentary rock. Okay, we'll take a look at each of these individually. Okay, so the first step I talked about was weathering and erosion. We have two ways that rocks can be weathered. The first one is mechanical or physical weathering. So this is the physical breakdown of the rock without any chemical change. So the minerals that make up the composition of the rock are not changing. You're just breaking it down into smaller and smaller pieces. So these are physical forces that I'll talk about breaking down into smaller and smaller pieces. Chemical weathering involves the chemical transformation of a rock into one or more new compounds. So you're taking the existing rock and it is being chemically changed. So something in it is changing chemically. One or more of the compounds in the rock are not the same as they were when they first existed. Okay, so let's take a look at each of these examples. So physical weathering can happen in the unloading process, which I'll talk about in a second, root wedging, frost wedging, or temperature change. So here is an image of a rock that started as a granite and it has been broken up into smaller and smaller pieces over time. Okay, so the unloading process is what happens when a pluton comes to the surface. So, my example here. So, when a pluton is below the surface, it is surrounded by pressure from all sides. So you can see this example down here with the dinosaur. Pressure is on all sides of this pluton, which is the circular shape here. And so pressure is from all sides. As soon as the pressure is released after it uplifts and erosion of whatever's on top of it is moved away, so all of this here is removed by weathering and erosion, then you have part of the pluton exposed, which is what forms those domes we talked about with igneous rocks. And those domes will then basically expand because there's no pressure holding them together anymore. So think of like a plastic bag. So I have a plastic bag here, and if I hold it in my hand with pressure from all sides, it's as if a pluton was below the surface, okay? Now, if I release that pressure, what is happening to the plastic? It's expanding. And that's because there's no pressure from all sides anymore. So that's the same thing that happens with the rock. Below the surface, it's got pressure from all sides. As soon as that is uplifted and brought to the surface, there's no longer pressure in whatever area is exposed, and so it starts to expand, and it cracks along these exfoliation joints. So we call them exfoliation domes because it looks like they're trying to shed its skin. Okay, so the unloading process is the process by which there's a reduction in pressure from the rock above being eroded away, okay? And we get these sheets, so you can see them in pretty much all of these images. You get these sheets of rock that look like they're peeling away, kind of like onions, or they're exfoliating on the surface. So we call them exfoliation domes along sheets, which are the layers. And the joints are basically the cracks from that expansion of the rock. Okay? So that's unloading. Frost wedging is when we see a lot of cycles of freezing and thawing that breaks down the rock. So in an area that has a lot of water and will freeze overnight, or in a certain time of year, you're going to see water seep into cracks, and that water, when it freezes, what does it do? It expands, right? So water freezes. When water freezes, it expands. So it expands and it starts to put pressure on sides of the rock, as you can see with these arrows. And that pressure will start to break the rock apart, and the rock will separate. And so then those broken pieces become part of a accumulation of like a talus slope at the bottom of a hill. So at the bottom of a hill or a cliff where material that has been eroded from its parent material falls and lands, we call that a talus slope. It's kind of a random pile of material that has eroded from the cliff face or from the mountain. Root wedging is similar to frost wedging, but instead of water, we're looking at plant roots. So any biological activity that is weathering the rocks is considered root wedging. Most plants are looking for water, right? And in very high dense rock areas where the rock doesn't have a lot of layers or a lot of vesicles or holes for water to fill, those are usually found in cracks. So water is going to sit in the cracks in the rock, and the roots will use those cracks to find the water, and then it goes towards those nutrients and it breaks that rock apart as it grows through the different cracks. So you can see an example here of a tree growing through these rocks, and you can see the rocks weakening and falling kind of off of this little hill here. Okay, so that's root wedging. So those are the physical weathering processes. Now we're working on chemical weathering. So chemical weathering can be oxidation, dissolution, or hydrolysis. Okay, and I'll talk about them individually. So oxidation is when something rusts. So in the event that there is a lot of magnesium and iron in a particular rock, if it's exposed to oxygen over a very long period of time, it will eventually rust and kind of turn this orange color. And so that rusting process of the rock is called oxidation. Okay, so here's a chemical equation for what you need in order to form oxidation. You need iron and oxygen, and that forms the iron oxygen that turns the rock this orangey reddish color. Okay, that ferric iron kind of color. Okay, so that's oxidation. So this happens when you have like hematite, limonite, or geothite. It also happens when you have hornblends. So this is a granite with some hornblends and some biotites. That's also common. Dissolution is the process by which rocks are being basically dissolved by acidic or slightly acidic water. So acidic water can be natural or it can be from pollution. If you see it over a vast area, this is from acid rain that was slightly acidic, from either the evaporation of acidic waters on the surface that was from pollution or natural, and then back down onto these rocks. So this will happen in rocks that are heavy in calcium carbonate, because calcium carbonate is a base and acidic water is acidic, and so it will kind of dissolve the rock. So here's a chemical equation for you. I don't require you to memorize these. You just need to know what the main constituents are, that you have some sort of acidic water that is dissolving the calcium carbonate rocks. So that would be like limestone. So we'll talk about what limestone is further on in this PowerPoint. But for now, just know that limestone is a heavy hitter with dissolution processes. These are the types of rocks that you would mostly see dissolution in. You can kind of see how it looks dissolved. And this creates a lot of karst topography where you see sinkholes and caves and things like that. We'll talk about karst topography with groundwater. All right, and then hydrolysis is the last type of chemical weathering. So this is usually common in silicate minerals that are unstable at the Earth's surface. So one of those unstable minerals at the Earth's surface is feldspar. And feldspar, when introduced to acidic water, will transform into kaolinite, which is a clay mineral. And so this process is known as hydrolysis. So it's changing one mineral to another mineral that's more stable at the Earth's surface. Okay, so as you can kind of tell with chemical weathering, a lot of these require water. Okay. Differential weathering occurs when a rock is more resistant or less resistant than a neighboring rock to the weathering process. So you'll see a differential weathering of the rock. So you'll see, for instance, this photograph has the top rock is not weathering as much as the bottom. It also has to do with wind position in this instance, but if a rock is more susceptible to weathering, it will weather faster than a rock that is less susceptible. And if they are side by side or near each other, then you're going to see something called differential weathering. Okay, so the second step in all of this after weathering and erosion is transportation. So once they break down into smaller pieces, then they have to be transported somewhere. Okay, and the transportation can be from gravity, wind, water, or ice. Okay, ice meaning glaciers. Glaciers do move through landscape or across landscapes, and they can take material with it. Wind can only transport very, very small particles, and water can transport anywhere from small particles to a lot larger particles. Gravity can basically transport any from the top of the hill to the bottom, and that's about it. And again, ice or glaciers can transport the largest particles. Okay, so when we're talking about particles, I'm talking about soil and sediment. So when the rocks break down from the parent rock and they weather and erode and are removed, they turn into what we call sediment. And sediment is unconsolidated pieces of rock, basically. So you have all these different particles of broken rock that have been altered by the chemical or physical weathering processes. Okay, so in nature, we have 4 basic sizes. It does get more complicated than this if you want to get into engineering or really into geology. We can talk about like a sandy silt and a silty clay and things like that. But for now, just for these purposes, we're just going to focus on the main 4, which are gravel, sand, silt, and clay. You've probably heard of these terms before, but just to reiterate, gravel is going to be your largest sized rocks or particles, which are going to be very coarse: boulder, cobble, pebble to pea size. So gravel is distinguished by these even more categorized sizes. And then sand, we have coarse, medium, and fine sand. Silt is going to be your next smallest size from sand, which can be coarse, medium, or fine. And then clay can either be coarse or fine. There's not really an intermediate with clay. Clay is the smallest particle, and gravel is the largest particle. Okay, so I want you guys to think about this photograph. So here I have a bunch of different sizes of rock, and I want you to distinguish between just A and B. We were just looking at A and B. Which one you think would be closest to the source, which one you think would be furthest, and what type of sediment do you think they are? So take a minute, pause the video if you need to think about what your answers might be. Okay, so if we're looking at sample A, I would say this is probably close to a coarser sand, coarse to medium sand. And then B, this would be more of a pea-sized gravel. Okay, so A would be a sand and B would be a gravel. Now, as far as closest to the source, we haven't really discussed that yet, but I kind of wanted you to get to start thinking about it. So as a rock is removed from the parent rock, you'd imagine that is the largest it will be in its journey, if you will, from being the parent rock to being a new sedimentary rock. So in this instance, I would say because B is a larger particle size than A, B would be closer to the source and A would be further from the source. But let's take a closer look at what that all would entail. So as grains are being transported, they become more and more round. So as you imagine, a rock that breaks off fresh from the parent rock is going to be jagged, it's going to be angular. And as it is transported either by wind or water or a glacier, it's going to start rounding itself out, right? So by the time it gets to the outlet of a river, it's going to be nice round river rock versus the bottom of the slope where it started and it just broke off into a random angular piece. So the closer to the source, the more angular the particles are going to be. The farther from the source, the more round the particles are going to be. So if you have rounded particles, you know that this rock or this sediment, is far from its source. Okay, sorting is another thing that plays a role. Sorting is what separates the different grain sizes in a sediment population. So the degree of sorting is measured by the transportation distance. So the further and further the sediment will move from the original location or the source, you're going to see better sorting. So it kind of drops out the larger particles. So when a rock is first eroded off of a parent rock, you're going to see very poor sorting in the sediment, which means that you have a bunch of different sizes. You have some large gravel sizes, you might have some almost sand-sized particles, some boulder sizes, and as you move further from the source, those larger sediments get dropped out because they can't be carried as far because they're heavier, they're harder to transport, right? So as you move further from the source of the rock, you're going to see better and better sorting where all of the sediment sizes are mostly the same. Okay, so remember, sorting is like sorting your socks. If all of your socks are thrown into the drawer, they're all different sizes and different shapes and different colors, they're not well sorted, right? But if you separate them all by size, shape, and color, then in your drawer you'll have a nice sorting, right? So sorting is the arrangement of the size, shape, and not color of the grains, but the size and shape of the grains, right? So poorly sorted would have a bunch of different sizes and shapes. Well sorted, they're all going to be fairly round and the same size. Okay, so what does this have to do with maturity of a sedimentary rock? So with a sedimentary rock, we are going to look at rounding, sorting, and size. And those all tell us something about the closeness to the source. The closer to the source a rock is, the more immature it will be. So at the start, when it first erodes from the parent rock, it's going to be angular, it's going to be poorly sorted, and they're going to be larger particle sizes. Okay, so we know that those are going to be close to the source, so they're immature. Okay, as they move further and further from the source, they become round, well sorted, and much smaller particle sizes. And those are mature sediments. Okay, So when we talk about a sedimentary rock being mature or immature, those are the things that we are going to be looking for: rounding, sorting, size, and closeness to source. Far from source is mature, close to source is immature. Think about it like moving out of your parents' house. When you're not very well rounded, you don't know what you're doing with your life, you're living with your parents, you're immature. Yeah? And as you grow up and start getting your own job and going to school and moving out of their house, you are farther from your source and you're becoming more mature. Same thing with sediment. It's a little different. Okay, so then moving on to the depositional stage. So this is the third step. So this is where the sediments start to drop out somewhere and they land either on a landmass, or they land in the ocean or a lake, or they stop in a stream and the stream dries up and turns it into a sedimentary rock. It's just depending on the depositional environment. So depositional environments are all over. We can see depositional environments in the mountains, we can see them in the desert, we see them in the ocean, we'll see them in glaciers. There's a lot of different places where we can see depositional environments, and it depends on the specimen that you're looking at will kind of give you clues as to where it may have formed. Okay, so we'll kind of talk about those different clues that you would look for. Okay, so I want you to look at these three samples here. So we have A, B, and C, and I want you to figure out, if you can, which depositional environment you think it formed in: riverbed, beach, or deep marine. Okay, so pause the video if you need and take a minute to see if you can figure this out. Okay, so a couple of things with these depositional environments. Riverbed, you're going to be looking for something like river rocks, right? So you've been to a river, hopefully. If you have not, go to a river, check it out. There are a lot of rounded kind of gravel-sized rocks there, right? Beach, you've been to a beach before, hopefully. If you haven't, go to a beach. And you're going to see a lot of like sand-sized particles there, right? There's a lot of sand at the beach. And then deep marine, in a marine environment, you're more likely going to see shelled organisms or some sort of sea creatures, right? So you'll see fossils in the rock. So if we looked at these three rocks, A, B, and C, which one do you think A would be? You see a lot of fossils in here, right? And this looks like the outline of a shell. So this guy right here, A, belongs to deep marine. That's its depositional environment based on the fossils and shells that you see in the rock. B has a lot of rounded gravels in it, right? So this kind of looks like river rock held together with some sand or something. So this would be your riverbed depositional environment. And then this one down here, C, looks like mostly sand-sized particles. So this would be your beach depositional environment. Okay, so then the last step is compaction and cementation, or the term lithification covers both of those terms. It's kind of a all-inclusive term. So this is the process by which sediment grains start to pack on top of each other. So they pile on top, and that increasing number of sediment that is piled on top smushes the ones or applies pressure to the particles below it. And so the overburden weight will compact the sediment. So we're not going out there and compacting the sediment like they do in construction. This happens naturally by the stacking up of the sediment and the overburden pressure from the sediment that piles on top of the other sediment. And so you see compaction of the grains, which decreases the pore space. So the space between all the grains as it's deposited will decrease with increasing compaction. And then those pore spaces will be almost completely eliminated once cementation occurs. So cementation can occur from a bunch of different things depending on the environment. So if you have a silica-rich environment, you'll see a siliceous cement. Calcium carbonate-rich environment, like in the ocean, a lot of the shelled critters are made of calcium carbonate shells, and when they die and then those shells start to break down, they will make kind of this carbonate ooze that can then fill in the spaces in the rock and cement the rock together. Or you might see an iron-rich cement, which will have a lot of, if there's a lot of iron in the environment, you will see the rock held together with the iron. All right, moving on to sedimentary structures. So when we look at sedimentary rocks, we're going to be looking at particular features they might exhibit, which also tells us something about how they formed. So in sedimentary rocks, they are laid out horizontally. So as those sediments stack up, they stack up horizontally. There's no reason for them to be vertical or any other fashion. And so those horizontal, basically lines that you can see in this rock are known as beds. So the layers of sediment are known as beds. And bedding is just saying that this rock has a lot of layers. Okay. So instead of using layers as a term, we use bedding, okay? And depending on the thickness, you might see a thicker bed for a particular portion of the rock than another. You might see a thinner bed. And that has to do with the amount of sediment present at the depositional time. So in a particular time, there might be more sediment available than in 1,000 years later when the next layer started to develop. Okay, so it depends on the amount of sediment present. Gives you thicker or thinner layers. Okay, so within beds we have formations. So when we can group certain sedimentary rocks together, we can group them as formations depending on their rock type, their age, and where they are formed. Okay, so here in the Grand Canyon we have a lot of different formations. A lot of people think that's all just the same rock, but it's not. You can see the layers or the beds within the canyon. And within the canyon, we have a lot of different rock types and a lot of different formations that formed at different times. Okay, and that's useful for geologists because we can look at fossils that are in these rocks. We can look at the age. We can look at incision rates of the stream and kind of give a history of how this area formed. Ripple marks can also be found in sedimentary rocks. So you can see symmetrical ripples or asymmetrical ripples. So ripples are from waves. Now, if they are symmetrical ripples, they are oscillating back and forth. Okay, so you have flow in both directions. So this would be like waves coming in and out and going out on a beach. Okay, so the symmetry here is looking at one individual ripple and saying, okay, the slope on either side is even, so they're equal. Okay, asymmetrical, one side of the slope is steeper than the other. And this happens oftentimes in a dune situation, so this could be wind or water. Water would be more like a river. Rivers have one directional flow, right? And so does wind until it changes. So wind, if you're looking at a dune, if you've ever seen maybe like Pismo dunes, they're not always the same, right? Because of wind direction, they move, they change. They're not always permanent, if you will. Whereas if it was solidified into a rock, it's not going to change that much, season to season. But because wind patterns change, dunes can change. But if the dune has been solidified into a rock, you will see the preservation of whatever particular wind pattern was present during its during its lithification stage. So we can make an assumption that, okay, if we've got an asymmetrical ripple here, that the gentler slope is the upwind direction and the steeper slope is the downwind direction. So you can kind of tell what depositional environment it came from, what the wind direction was at the time of lithification, and maybe what type of environment it formed in. So remember, asymmetrical ripples are one-way direction, symmetrical ripples are oscillating back and forth. So here's another example of the dunes I was talking about. These are the Death Valley dunes. So the wind direction is on the back side of the dune here, where the gentle slope is, and the downwind direction is where the steep section is here. Okay, and once this is transformed into a rock, you would see something like this. Okay, and normally in a hand sample in lab, you'd be able to run your hand over the sample and tell whether one side is giving you more resistance, which means it's steeper than the other side, or if it feels the same, then that would be symmetrical. Okay, next is mud cracks. So mud cracks form when you have mud, water, and rapid evaporation. So you've probably seen these throughout the Central Valley before because we oftentimes get a lot of water, sometimes fairly quickly. Recently it's been these really interesting downpours. And then because it's so hot here normally, the weather will change drastically and then you'll see rapid evaporation of everything when the sun comes out. And that will form kind of these cracks in the mud that you see. And that's what they are, mud cracks. And if they are preserved over time into rocks, you will see either a cast or a mold of it. The mold would be the actual crack. So it's the actual solidification, lithification of the mud into a rock, and it's a mold of it. If it has filled in, so let's say this was mud cracks and they filled in with sediment that then turned into rock and then it was separated, that would be the cast. So the cast has the raised ridges and the mold has the impressions or the depression hole features that are indicative of mud cracks. Okay. Cross-bedding. Cross-bedding is when beds cross. So instead of being horizontal, the beds will cross in something like a dune environment. So this is similar to like the ripples, but here it's a little bit more of a wispy feature that we're looking at. We're not looking for waves necessarily, which are what the ripples are. So in this instance, we see when wind blows over a dune, it picks up material from the upwind side and deposits it on the downwind side where the steep slope is. And because of its deposition, it kind of collects in these, so this would be like time 1, 2, 3, 4, 5. It kind of just accumulates like that, and it creates these beds that have an angle from the original horizontal bed. Over time, depending on wind direction, if it changes, it'll kind of have crossed cross beds. Okay, so this master bed here is the original horizontal bed that I was referring to. So let's look at a little animation of that. So here we see the wind from the upwind side picking up material and then it's depositing it on this downwind steeper slope section of the dune and accumulating all of the sediment in kind of this angle instead of being horizontal, and creates these really amazing cross beds that can be very large in size or they can be very small. I found this when I was field mapping a long time ago, and you can find these really microscopic looking cross beds, or they can be, intermediate in size. Okay, moving on to graded bedding. This happens in a turbidity current. So when a underwater landslide occurs, so let's say we're looking at the continental shelf off of the coast of California, if a landslide would occur underwater, all that material that was on that slope is then fluffed up into the water column. So it's like putting a bunch of dirt sediment into a bottle and then shaking it up. What do you think is going to happen? Well, the material that is coarser is going to drop out first. So everything that's the most dense is going to fall to the bottom first, and then the finer stuff will start to accumulate. So it basically arranges the grains by size because of the density differences. So in a rock that is solidified, what's really interesting about graded bedding is that you can tell which direction is up, even if you don't have the sample in the field anymore. You can have it in the lab and tell which direction is up based on where the larger particles are. So the larger particles are down here at the bottom of this photograph, and it gets finer upwards. So these are the larger particles that dropped out first, and then the smaller particles started to accumulate because they're closer to the density of water. So the water is what is controlling the dropout in density. So the gravel will drop out first, and then you would see sand, silt, and then finally clay. And so your clay would be up at the top if it existed in the rock. And so in this particular rock, you can tell that up towards the top of this page is the top of the rock or top of the formation because of the density difference in the rocks or in the sediment that's present. So here's another look at that. Here would be the shoreline of, say, the California coast. On the continental shelf here, we see submarine canyon that has released a bunch of sediment from an avalanche or landslide. All that sediment gets thrown up into these turbidity currents where all the sediment is now in suspension in the water. And then eventually, as time increases and the turbulence slows down, you start to see the dropout of the larger particles and then finally the smaller particles. And they arrange themselves from largest to smallest, from bottom to top. Okay. All right, so looking at environmental clues in sedimentary rocks, that'll kind of tell you something about where they came from. So we talked a little bit about this when we talked about depositional environments. This is going to give you a little bit more information. So when you see fossils in a rock, by the way, sedimentary rocks are the only rock you're going to see fossils in. We haven't talked about metamorphic rocks yet, but metamorphic rocks are formed by heat and pressure. Fossils cannot survive that. And igneous rocks are formed from molten magma. Fossils can't survive that. Sedimentary rocks are where you're going to find your fossils. So any fossil found on Earth is found in a sedimentary rock, period. Okay, so if you have fossils in a rock that you're looking at, you know it's sedimentary. Okay, so if we see corals and echinoderms or something that you know is from the sea, you're going to be looking at a saltwater depositional environment. So you know that rock came from saltwater or a marine environment. If you see things like insects and amphibians, you know that that came from freshwater on land. And then if you see leaves, land animals, things like T-Rex or dinosaurs, you know that that is terrestrial. Okay. Color and chemistry also give some clues. So if we see red beds, like this photo here, where the rocks look a little bit red, those are often terrestrial. So those are found on land. Terrestrial meaning land. Black shale, if we see anything that is a shale-sized particle, or a silt-sized particle, excuse me, which is shale in a rock form, and it's a very dark black color, that's usually found in oxygen poor or very, very deep water where there wasn't a lot of air or oxygen present. If we see evaporites, which are when water is evaporated really, really quickly, it leaves behind these little salt pockets, and they form something called an evaporite, which I'll talk about in a second. Those are usually formed in an arid climate, so this would be terrestrial, but it would also be a very dry area, so like a desert. Okay, so those are some clues that you can use to tell where your rock formed if you're looking at one. Okay, so we have two classifications of sedimentary rocks. We're looking at the type of sedimentary rock, and then we're looking at characteristics. Okay, so how we characterize sedimentary rocks, I'll talk about in a second, but type is the first step. So we're going to look at whether they're clastic or they're biochemical, and then characteristics depends on whether they're clastic or biochemical. Okay, so our clastic rocks are made of fragment material. So these are the ones that are made of sediments. Okay, and they're deposited by water, wind, glacial, and gravity. The biochemical sedimentary rocks are the ones that are formed either from evaporation, precipitation, or they have biogenic sediments. So this biogenic sediments would be like plant fragments that have broken down, weathered, and eroded, and then solidified and formed into something like coal. Okay, so that would be like a biogenic sediment. Okay, so clastic sedimentary rocks are classified by grain size, texture, and grain composition. So grain size is what size particle are we looking at? Gravel, sand, silt, or clay. Texture would be, is it coarse, fine, or medium? And then grain composition would be, what type of grains do you see in it? Okay. So remember, we have clay, silt, sand, and gravel. Here are the grain sizes that are equivalent to the sediment name. And then these are the rock types that you'll see. So a clay will make a shale, a silt will make a siltstone, and a sand will make a sandstone. A gravel will make a conglomerate or a breccia. We'll talk about that in a second. But these are the basic rock types that will be formed from the basic sediment sizes. Okay, so we have arid detrital, or this is also clastic. Okay, so this is our clastic side. So if you're seeing coarse grains, so gravel size, you will either have a conglomerate or a breccia. And you need to take a closer look at whether the gravels are angular or round. If they're angular, we consider it a breccia. If it's round, we consider it a conglomerate. Okay, these are different from the breccias found from volcanic igneous rocks. Those are held together by ash. These will not be held together by ash. They're held together by other sedimentary particles. Okay. If it's a medium size, then we're looking at sand. So that would be a sandstone. Okay, and there are special sandstones that I'll talk about in a couple slides from now. If it's fine grained and looks like it has silt in it, I know this says mud. It's a little bit more general than I'd like. If it has a silt-sized particle, it would be siltstone. And then if it's very fine and has clay-sized particles, that would be shale. Okay, and then moving on over here to our biochemical sedimentary rocks, these have some sort of chemical or biological component. So the biological component would be the coal down here, the bituminous coal that you can see. And that is made from altered plant fragments. And that's going to be very dark in color and very low density. So it's not going to be very heavy. And then here we have this really big section that has calcite or calcium carbonate in it. If it has calcium carbonate in it, it's going to react with acid. Okay, and if it reacts with acid, it tells you that you need to look at the rocks in this section. Now, then it's defined by texture. Okay, so if it reacts with acid, we automatically go to this section. Okay, so then we go, okay, is it fine to coarse crystalline looking? Okay, then it might be crystalline limestone or travertine. The difference between crystalline limestone and travertine is that travertine is layered. Crystalline limestone is more interlocking looking, so it doesn't show particular layers of the crystals of calcite. Okay, if it has a lot of shells in it, and then you're going to be in this biochemical limestone section here. So all of these will contain shells. If they're microscopic shells, they're chalk. Okay, chalk is going to look like chalk, but it's made of microscopic shells and clay. If it is loosely cemented shell fragments, that is coquina. If the shell fragments in it are well compacted, that would be fossiliferous limestone. Okay, so those are how to tell the difference between all of your calcite-bearing sedimentary rocks. Now, if it has quartz in it, you're looking at either chert or flint, and the only difference here is their coloring. Okay, and quartz is going to look kind of crystalline, and it will scratch glass. Gypsum will be really easy to scratch with your finger, just like the mineral gypsum was, and this would be rock gypsum. If it has halite in it, it's going to be very salty, and it usually is formed in kind of like these very nice cubes. So you'll see a bunch of cubes kind of stacked up together, and that forms rock salt. Rock salt is an evaporite, so it's formed from the rapid evaporation of water in a desert environment. It deposits salt, or NaCl, sodium chloride. Okay, so let's think about all these different sedimentary rocks we have here. So I want you to look at all these different samples. They're all labeled. I think there's one behind there. Okay, so they're all labeled here what they are, but I want you to start thinking about whether they have grains, fossils, do they maybe look crystalline? Do you think that they're clastic or chemical? And if you need to, you can pause the video before I move on. Okay, so take a minute if you need, and I'll talk about it. Okay, so if you didn't notice, the biochemical sedimentary rocks are in this section, and the clastic sedimentary rocks are down here on the bottom. So what you would look at is, do they have grains, fossils, or do they look crystalline? So all of these guys down here on the bottom look like they have grains, or they look like they're made of sediment, even if they're fine, like the shale and the siltstone. Okay, so they're made of sediment, and the conglomerate and breccia are made up of the larger gravel-sized particles. Notice that the conglomerate has the rounded particles, and the breccia has the angular particles. And then sandstone is made of sand, and oftentimes sandstone will also feel like sandpaper. Okay, the biochemical sedimentary rocks, chert is made up of quartz, travertine is made up of calcite. This is the layered travertine that I was talking about. Limestone is well compacted shells. Coquina is very loosely compacted shells, and then the bituminous coal is made up of the altered plant fragments. Okay. So by crystalline, just to clarify, chert and travertine would be your crystalline look. And then these guys here, limestone and coquina, are showing fossils, and then coal, it looks like carbon, right? It looks like plant fragments that have degraded and been compacted, and that's what that's made of. And then all of these down here at the bottom show grains, so they show the sediment grains. Okay, so this is just another look at that. So we had all of these on here, all of your classic sedimentary rocks. I didn't show you crystalline limestone, chalk, flint, rock gypsum, or rock salt. But if you're curious, you can always, I don't think your book has them, but you could always Google images of them so you can kind of get a reference point. So some special classic sedimentary rocks. So these are both sandstones. If it's a feldspar-rich sandstone, it's going to be kind of a pinkish, reddish color, and we call those Arcos sandstones. And then if the sandstone is fairly angular, which isn't as common in a sandstone, most of them are rounded sand grains. If it's angular and immature, we call it a gray wacky, and oftentimes it is gray as well. Okay, so moving back to the rock cycle, here it is complete, and we haven't gotten to metamorphic rocks yet, but you want to jot this down because this is really important when we're talking about rocks. So at the top we have igneous rocks. In order to form a rock and to move in the rock cycle, you need to know how each of the different rocks are formed. And so you can go from one rock to another. So rocks move in a cycle. They do not stay in one particular rock type forever. So an igneous rock can become sedimentary as long as it goes through the weathering, erosion, transportation, deposition, and lithification processes. A sedimentary rock can become metamorphic as long as it goes through heat and pressure. A metamorphic rock can become igneous if it goes through melt, cooling, and solidification. And vice versa. An igneous rock can become metamorphic by going through heat and pressure. A metamorphic rock can become sedimentary by going through weathering, erosion, transportation, deposition, and lithification. And a sedimentary rock can become igneous by going through melting, cooling, and solidifying. And they can all start as an igneous rock. A rock can start as an igneous rock and be further melted, cooled, and solidified and become a different igneous rock. Same thing with the other two. Metamorphic rocks can experience more heat and pressure and become a new metamorphic rock. Sedimentary rocks can be weathered, eroded, transported, deposited, and then lithified, and then become a new sedimentary rock. Okay, so the rock cycle is a flow, and you're going to want to make sure that you know this because this is really important for this course. Okay, so that's the end of sedimentary rocks. Next up is metamorphic rocks, and I will see you guys in the next video.